All right, in the last example, we saw that R2 has different bases. In fact, I said that any non-trivial span will have infinitely many different bases. So bases, although bases themselves are not unique, once you have a fixed basis for your span S, so once we've chosen a basis, any vector of S will be expressed in a unique way as a linear combination of the elements of B. All right, so this is theorem 7.4.1. Let's spell this out. Let B, which is a set of vectors from V1 to Vk, be a basis for S. Let W be any element of S. There are unique, so that's the unique way, real numbers A1 through AK, so that W is A1 V1 plus AK Vk. So it's a linear combination with A1 through AK as coefficients. All right, so I want to prove this. I'm going to need to prove two different things. I'm going to need to prove that these A1 through AK exist and that I don't have a choice. There only is one way of doing so. All right, so let me start with existence. B is a basis for S. That's what I'm given. That means by the first condition, S equals span of B. So W is in the S, so it's in the span of B. And if I spell out the span of B, just to remind you of what it is the set of all linear combination. And so, of course, that means that W can be written that way. For some A1, AK, and R. So this part is more straightforward. We know that W is in the span of B, so we know it's a linear combination. All right. The second part, the part that's more interesting, is the fact that I don't have a choice. There's only one way of writing W in terms of B. All right, so let's assume we have two ways, not two different ways, just two ways. So assume that W is A1 V1 plus, let me put in AI VI plus AK VK. But also W is B1 V1 plus BI VI plus BK VK. All right, so let's assume that I have two different, one and two ways of writing, not different, two ways of writing W as a linear combination. So what we want I want to show that AI equals BI, all right, for all i's. All right, so really these two seemingly different ways of writing W as a linear combination are exactly the same. They're just labeled differently. All right, so what I'll do is I'll take the equation 1 and I'll subtract the equation 2 for it. So I'm taking this minus this one. All right, so I'm going to get on the left, I'm going to get W minus W. On the right, I'm going to get A1 V1, AI VI, AK VK, and I'm going to subtract the ones with the B's. Now, if I rewrite this on the left, I'm just going to get 0. Then on the right, I'm going to put all the V1s together. I'm going to put all the VIs together, and I'm going to put all the VK together. All right, so for V1, I get A1 minus B1, so this and this. For VI, I get AI minus BI, and for VK, I get AK minus BK. All right, so what I'm getting is a way of writing 0 as a linear combination of V1 through Vk. Now, this is where we're going to use the second condition. So since B is linearly independent, we know it's a basis, so we know it's linearly independent. That tells us that there's only one way of writing zeros in linear combination. So only the trivial solution works in 0 is C1V1 plus CIVI plus CKVK. All right, so that means this has to be 0, this has to be 0, this has to be 0. So if I apply this to our linear combination up here, that's going to mean that each of this coefficient will need to be 0 as well. So A1 minus B1 will be 0, AI minus BI will be 0, and AK minus BK will be 0. And so that means A1 equals B1, AI equals BI, AK equals BK. And so when I said we're going to start with two seemingly different linear combination, they turned out to be just the same because B is linearly independent. And so, yes, these coefficients are unique.